Hello, this is Alan Fern, and I'm going to tell you about our work in the Machine Common Sense DARPA program. My team involves a number of people. Now, I'm tentatively naming this talk Model-Based Reinforcement Learning, Perspective on Common Sense Learning. Not sure if that's the greatest title, but it kind of describes what I'm going to talk about. The team involves 5 people from Oregon State. We also have a collaborator in robotics, Tucker Hermans from the University of Utah, and from developmental psychology, Karen Edoff from NYU. So it's a diverse team, and we're just getting started. We've been in this project for about a year now, and I'm really going to try to, instead of getting into a deep dive of certain details, I'm going to give you a flavor for our approach and touch on some of the details, but not get into anything too rigorously. So I'm happy to answer questions about any details that are missing here. So the first thing I want to do is just review the questions that sort of motivated our approach. And so the first question that we have to answer when anyone is studying machine common sense is, how do you characterize common sense? Second question is, what innate reasoning and learning primitives do we want to use for our machine common sense systems? And then, what architectures do we want to use for these systems that are going to exhibit some form of common sense? And finally, how are we going to train those architectures? How are we going to generate training experience, and what learning mechanisms are we going to use? So I'm going to go through these quickly one by one. And we'll start with, how do we characterize common sense, which is always a fun thing to talk about. We could talk about this for days over beers, I'm sure. But for the time being, in our project, we think of common sense in this way. So it's the set of obvious deductions made quickly and easily by most members of a population when behaving in their environment. And I've highlighted two key terms in this definition, obvious deductions and when behaving. So let's look into these. So when I say obvious deduction, what I mean is it's some reasoning process that seems to require little or no deliberation or reasoning. So it's really a consequence of reasoning that seems to require no deliberation, no real thinking. And this is really a computational concept. And if you're a computer scientist, you might think polynomial time, right? So it's efficient in the sense that the consequence can be derived in polynomial time as opposed to requiring exponential time search or deliberation. And this viewpoint is inspired heavily by these two papers and a few follow-ups by David McAllister and colleagues, where he really tried to characterize common sense judgments in a formal way via this notion of polynomial time versus exponential time search. And I won't get into the details of his work, but I'll show you a couple of just examples of what we mean by obvious deductions in that sense. So here's a picture of a king on a chessboard. And most of you probably know that a king can move one square in any direction. And I can ask you the question, can the king reach every square on the chessboard if I give you any number of moves? And I would say that for most people, the answer is going to be obviously yes, which you did not have to think about this in detail, even though at some level it involves a form of mathematical induction in your head. But nonetheless, it's an obvious deduction for most humans. Now, I could also ask you about a knight. So the knight has a strange one-move pattern. This is the places it can go in one move. And I can ask you the same question. Can the knight reach every square on the chessboard? And maybe some people see this immediately, but I sure don't, and I don't think most people do. The answer is yes, but it's not obvious. You would have to come up with an argument. to convince somebody else. You would have to think to convince yourself, most likely. So we're going to call this non-obvious. And McAllister's work was all about trying to come up with representations of logic that, for example, modeled natural language, where the obvious consequences from those representations would entail things like this king question versus the knight question, which would not be entailed. Just another example. Here's a maze. Is it obvious how to get from the beginning to end? Yes, it is. That was pretty clear. You didn't have to think much. Now this one, even though in a few seconds you might figure out the answer, I'm going to say that this is not obvious because of those few seconds where you did have to think and deliberate, and you might have even run into dead ends. So that just gives you a flavor when we say obvious versus non-obvious, what we mean. We just mean immediate thinking, and this is similar to the System 1 type of idea in System 1, System 2 terminology. Now, so that means that we're interested in these in common sense as efficient computation, but now let's talk about the when behaving part of the definition. What is the purpose of common sense reasoning? Well, we decided that the purpose is exclusively to generate effective behavior, and in particular, efficiently generate effective behavior. What good is common sense if it's not used to generate behavior? It's not good at all. There's no utility in it. So we really take a behavioral viewpoint in our work. And this suggests a test for infinite level common sense, which we are interested in infinite level common sense in our project. And the test can mainly be, can you efficiently produce observed infant behaviors based on direct environmental input? Can your system do that? And if it can, we say that it has infinite level common sense, because it would have to make the same types of obvious deductions that infants have to make to perform those tasks. So efficiently walking across a room, or picking up an object, or finding an object that's been hidden or put in a box. Now, this is quite different than an approach that may be based on core knowledge, where the test would be in terms of seeing whether the system somehow, either through indirect or direct testing, captures some presupposed core knowledge concepts. And that type of test has some problems, also has some interesting aspects to it. But how do you know when you've actually covered all the core knowledge concepts? Well, you really don't until you actually see, hey, until you could actually say something to the effect of these concepts are sufficient for producing the behaviors of the infant. So that's how we're going to characterize common sense in this project. That's sort of our guiding principle. And now we can come to the question of what are the innate reasoning and learning primitives that we want to use for machine common sense. We have to start with something. So what are those things going to be? And you can think of this as, in the human case, what is innate in the development of humans? What was built in? So we're going to ask the same question here, and I suspect the answer is going to be quite different, because we have to actually engineer these systems, which are very, and our engineering tools are very different from biology. So, our starting point is that over the years, the last 50 years, AI research has developed powerful solvers or algorithms for a variety of types of problems. And these solvers can produce, in concept, many obvious deductions given the appropriate input knowledge. And these deductions are nice because they really give you a generalized reasoning capabilities across different goals and environments. You don't have to relearn anything. If the goal changes or the environment changes slightly in a describable way. These solvers can just be reapplied to solve the new goal or the variant of the environment. So we'd like to leverage these if possible. And the question is, which ones should we leverage as the innate primitives? And well, I guess you can also ask if we should do that at all. Like there are other points of view that would say, no, you should just not use any of those innate reasoning primitives. It's all learning, for example. But I think it's a very valid question to ask. What are the innate reasoning primitives, even in human infants? That might give us insight into to what we might select here. And just as an example of what one of these primitives might be, I'm showing you an example here from our work where down below, down bottom, there's just an image of a simulated robot moving around a playroom, you might say, and there's the RGB image that gets read in by the camera, and then there's also a depth image here. So you have a little bit of depth information. And we're going to hook up a symbolic planner to this environment. And a symbolic planner, this particular name is metric FF, takes in a state, which is an abstract state. It's these logical facts, symbolic facts, you could say, about the world. The hand is empty, for example. And it also takes in a goal. You want the apple 1 to be on top of chair 1. And then it also takes in a description of actions. So these describe the preconditions and effects of actions and the parameters to them. And given all this, it will output an abstract plan over these high-level goals, which is at some level of abstraction that sort of makes sense from a higher-level reasoning perspective. So if we have a system like this hooked up, and I'll mention how that might be hooked up in a moment, this is what we did for one of our DARPA evaluations. Here's an example of we asked the system to get 3 objects onto that chair, and you'd like to do it efficiently. Now, a person might look at that scene and say, hey, I can only carry 1 object at a time. So how about I put the 3 objects in the box, in the container, and bring the container over? Now that's a pretty common sense type of thing. What age level would an infant realize this? I don't know, but it's not going to be. You're not going to have to be too old to understand basic container usage. And so we see the planner just automatically figured that out. And the cool thing about the planner is it could do this for any variety of this type of goal. So you might want 3 things over at that chair, 3 things over at the other chair, and you have 2 containers, and it might use them both. Who knows? Now, I'm not going to go through this video, but this is a similar video where there are 3 objects that should be on a nearby chair. The same planner is being used, but it figures out that it's not worth putting the objects into the container and bringing the container over. The objects are close enough that it just puts them directly on the chair. So this is also a common sense concept if you're trying to be efficient about achieving your goals. So the problem with all of this is the grounding problem, right? So this is a problem in the sense that these abstract actions and these abstract states aren't really connected to the raw pixels of the environment. And so what we had to do is build an encoder that takes the pixel data and abstracts to a state. And likewise, you have to take the symbols for the actions and decode them into actuations for the robot. And at this point, a lot of people would say, checkmate, these symbolic AI solvers are done, dead, they can't interface, and so let's throw them away, let's just learn everything from scratch with neural networks, for example. And that's we'll put that on pause, but assuming that you do declare checkmate, we can talk about what are the innate learning primitives for an MCS system. And for this, you might look to the modern advances in deep neural networks, which have produced really great advances recently. So they can produce obvious deductions like classifying objects from raw inputs, which are similar to the training data. So that they're very biased by the training data, but that can be really huge and enormous. And the effectiveness does depend on human design structural priors. So, for example, deep networks for image recognition rely tremendously on the prior of convolutional units in these neural networks that give you a sense of translational invariance. And then there are other types of priors that are built in as well. And so the questions here, should we include neural networks, as innate primitives for MCS? Seems like a reasonable idea. And if so, what structures should be the ones that we choose as the primitives? Right. So that's what I'm going to say there. I would say that I think trying to use reinforcement learning technology, for example, to with deep networks to get the type of generalized reasoning behavior that you just saw, even the simple reasoning behavior, is very difficult. You might be able to do it if you just restrict to that environment and a small set of goals, but then I'll be able to give it a goal that the symbolic planner would be able to nail easily, but the neural network wouldn't be able to understand. So that brings us to the architecture question. What machine common sense architecture should we start with? And our team is going from the point of view that we should leverage AI solvers. So let's select a small set of primitive AI solvers. And also let's select a small set of primitive neural network structures. Right, so this is quite general. I'll give you a specific example in a moment. And then, but really these choices are a major point of research. And then what we'd like to do is use the neural networks to learn grounded knowledge for the AI solvers. Right, so that if there was a research task and challenge that sort of encompasses our project, that would be it. Using neural networks to learn grounded knowledge for AI solvers. And this allows you to exploit the AI solvers to support general purpose reasoning that goes beyond training data in the specific situations and slightly generalized situations from the training data, but to really go beyond it. And it also allows you to leverage neural networks to support the knowledge grounding. So there's a huge amount of work there that needs to be done. Growing interest in this is growing quite fast under different names, although I think a lot of the AI solvers are still not really being used in this sort of framework yet. So I want to give you a simple example, but one that I think we can develop into a fairly powerful system. That's what I've currently got a student working on this, and I'm really curious to see how far we can push this. So I'm going to show you an example from this first-person navigation example where the input are these pixel first-person images of a robot. And what we do is we collect all this prior experience running around the world, and we use a neural network, won't get into the details, to learn a latent representation, an internal representation of the state of the environment. And we use that representation to create this finite Markov decision process that encodes this abstract model of the environment. And roughly speaking, the nodes of this environment are latent representations of some of our experiences, maybe all of them. Maybe it's 1 million nodes here of experience, and the latent representation, we have one node for each one. They're connected in a certain way according to the dynamics that were observed. But however this is done, you may end up with an abstract model that has millions of states, and you can think of it as a type of episodic memory, which is a term that might resonate for people. and it combines the memories into abstract models that can be used for planning. And in particular, we use a very simple planning algorithm right now to generate plans, which can leverage GPUs because of its simplicity, which is a major advantage. And this is called value iteration. It's a fairly generic algorithm. But that's basically it. And we can actually prove some interesting results about this type of model. And when new observations come in, we can without doing any replanning or anything like that, we can just or collecting new data, new learning, we can just map those new observations to the nearest abstract world state and generate the correct course of action. And nearest is based on the learned representation. So I'm just going to show you a few examples from this. So here it's a simple task, but again, it's from raw pixel data, first-person pixel data. And the task was to, get to that box as quickly as possible. The input is just this first-person perspective. This is an overhead map showing you what it's doing. And it's learned a pretty good policy here. Now, just to show you some of the generality of taking this symbolic neural approach, if you were to sort of take away the ability to turn the cart to the left and just have the system do no more learning, just use its understanding of the dynamics to figure out what to do. Here you can see, it's still able to achieve the goal, just doesn't turn to the left. Same thing with turning to the right. Right, so that's just showing you some of the generality that you can get, and you can imagine that a young child, maybe even an infant, if you gave them a car to play with and then you took away the ability to turn it one way, they would still be able to reach locations. It would take them longer, but they would still be able to do it. And I think I will skip over this next example. It's just showing you another form of generality. I'll point out it can even play Atari games, which was nice to see. So now, getting low on time, so I'll just very quickly cover this. How do we generate training experience and learn for this architecture? Well, we're going to leverage infant behavior data, working with our collaborator Karen Adolph, and one of her projects called Databury, which has tons of video of infants and young children playing in different experimental environments. And by analyzing this data, we can try to come up with staged training curriculum of what behaviors are exhibited at each stage, and then train our simulated robot, we'll say, in an environment to achieve those behaviors in those stages. And the second thing that we're going to do with the infant data is to use them to learn exploration strategies. So infant-inspired exploration strategies. How do infants explore an environment? How do they play? Maybe there's something to be learned for our machine learning systems if they could sort of play like infants play. And so I'll skip over some of the details. We're developing models of exploration. This is just showing you infants playing with different toys in a room and the toys they choose over time. You can see there's very different patterns. It's very interesting over time. And so learning models of these and driving our simulated infants with these models is something that we're looking into right now. And with that, I think I'll just leave these questions up.